Humans have functioned for hundreds of years using fossil fuels to run their society, but the Earth has survived many millennia more. The continued use of fossil fuels has begun to cause destructive changes to our climate. The non-renewable energy emissions are mainly greenhouse gases, which when built up in the atmosphere cause problems such as global warming, climate change, and unpredictable weather anomalies. This is not only a threat to the Earth and the humans that live on it, but these fuels are also being depleted much faster than they are being produced. When they run out, society will be forced to find alternative energy sources. Since we cannot viably remove large amounts of these greenhouse gases from the atmosphere, the main way we can combat this problem is to use alternative energies. You know that big ball of radiation we call the Sun? It has burned for 4.5 billion years, and for all the time that life has been on Earth, the energy from the Sun has sustained the planet. Plants use photosynthesis to capture the energy from the Sun and use it to produce sugars and do other biological processes. The Earth absorbs 3,850,000 exajoules, that's times 10 to the power of 8 joules worth of energy every year. Working through, the Earth absorbs just under 40 exajoules per hour. This is more energy per hour than the Earth currently requires yearly. The point is that there is so much untapped energy being flung at us, it seems illogical not to utilize it. Much renewable energy, either directly or indirectly, absorbs power from the Sun. Solar panels are the most obvious choice for capturing the Sun's energy. There are two different kinds of solar panel: photovoltaic and steam generators. Photovoltaic cells generate electricity directly from sunlight. As photons are incident on the solar panel, an anti-reflective coating prevents unnecessary reflection and then hits a thick semiconductor layer. Electrons in this layer are promoted to higher bands and generate a potential difference across the two contact plates. This directly produces an electric current. Another way to harness solar energy is to use a large array of mirrors to concentrate sunlight on a water tower. The sunlight evaporates the water to produce water vapor. This pressurized steam then drives a conventional turbine around to produce electricity. Unfortunately, there are some drawbacks to solar panels. They are fairly inefficient, with photovoltaics only absorbing about 11 to 15% of the light energy available to them. In addition, the rotation of the Earth means that sunshine is not available to solar panels at night. Without light, there can be no energy produced by solar cells. Fortunately, the Sun has other effects on the Earth. As well as providing light, it provides heat via the radiation. This heat causes great convection currents across the Earth. This is experienced as wind, and the best way to capture the energy in wind is with wind turbines. The simple movement of air across the blades pushes them around. This in turn spins a magnet inside a coil of wire to generate electricity. After the initial construction and installation costs, this is effectively free energy, since these turbines have a lifespan of about 20 years and do not require much maintenance. Unfortunately, these share a fatal flaw with solar panels in that they do not generate electricity when the wind isn't blowing. One of the oldest and most powerful forces on the Earth is water, a tsunami levelling a city, or a broken dam barreling down a hillside wreaking untold damage. Imagine harnessing that energy. We may not be able to hold back the tide, but we can use it to our advantage. The movement of water is ideal for turning a turbine to generate electricity. There is awesome power in these technologies, but this kind of electricity generation has environmental problems associated with its use. Not only do dams flood large areas of land, affecting habitats and forcing animals and people out of their homes, but it also reduces water flow downstream, affecting water supply to habitats from the dam all the way to the sea. Turbines can be implemented in rivers to avoid the damage to water supply, but these can prevent the movement of wildlife up and downstream. Hydroelectric sources of energy are also very dependent on the geography of the surrounding area. If the land is not suitable, then a dam cannot be built there. Geothermal energy is one of the more hidden renewable energy sources. It is geographically dependent on radioactive rocks deep underground that produce heat, and lots of it. Countries like Iceland have good access to these rocks in the form of geysers. Water is superheated by the radioactive rocks and becomes gaseous and very pressurized. This is then forced back to the surface and is released as an explosive plume of water. When done in a controlled manner, this steam can be used to turn turbines. Much of renewable energy involves the use of turbines to generate electricity directly. If you can turn the turbine, you have electricity. The issue is that none of these technologies can provide a reliable source of electricity at all times for all the world. But together, perhaps this is possible.
Moving on to biofuels. So what is a biofuel? A biofuel is a renewable energy carrier that can store the energy derived from organic materials such as biomass, including plant and animal waste. Some backstory on biofuels is that they've been around for a very long time, dating back to the early 19th century when scientists found that vegetable oil could be used as a fuel. It was also praised by Rudolf Diesel when he said that these oils were almost as good as the fossil fuel-derived alternatives he was using at the time. Biodiesel was first produced in 1937 by a process called electrolysis, which used vegetable oil and ethanol to make biodiesel. These are just some of the feedstocks used, the main ones being soybeans and rapeseed. This is the equation for the formation of biodiesel. It's the addition of a fat plus alcohol to make an alkyl ester, which is a biodiesel. The advantages of biodiesel are that when compared to diesel, it produces less emissions overall. It can also be blended to form B20. By using biodiesel, you reduce the maintenance cost of your engine because it lubricates the engine, which allows less dirt to build up. One of the issues with biodiesel is that its performance is slightly lower of diesels, however it is slightly higher than petrols. The main issue with biodiesel though is to do with the feedstock. Deforestation often occurs in countries such as Brazil for the land. Many think that this farmland should be used to grow food, not fuel. Another biofuel is ethanol, which is mainly sourced from corn. The fermentation process within an ABE fermenter also produces other chemicals such as butanol and acetone, with butanol being another biofuel. Ethanol fuel is already in large-scale usage by being blended with petrol to form blends, the most common being E10. The energy E10 produces is very close to petrol. Despite biofuel being more efficient than that of petrol and ethanol, its production is low, partially due to the cost of producing the fuel being higher, and there is also less availability compared to petrol. In conclusion, I believe that if the cost of biodiesel production are reduced, and if a feedstock which uses less land is found, that it should be the main fuel due to its good efficiencies and reduced emissions compared to the current fossil fuel-derived fuels.
Nuclear fission is a process in which the nucleus of an atom splits into lighter nuclei, releasing a large amount of energy in the process. This phenomenon was discovered in 1938 by Otto Hahn and was explained a year later in 1939 by Lisa Meitner and her nephew Otto Frisch. This process is achieved by bombarding the nucleus of a heavy atom with a fast-moving neutron. This results in a large nucleus splitting, forming usually two lighter nuclei, additional neutrons, and giving off large amounts of energy, typically in the range of around 200 megaelectronvolts. The most common type of fission reactor is known as a critical fission reactor. This type of reactor works via a chain reaction mechanism. The neutrons produced by the fission of fuel atoms are used to induce more fission reactions, leading to a chain reaction of fissions, all producing energy and more neutrons. Uranium is the most common fuel source for fission reactions, with the uranium-235 isotope being the one used, as opposed to the uranium-238 isotope, which is the most common. Uranium-238 accounts for around 99.3% of naturally occurring uranium, while uranium-235 only accounts for 0.7%, meaning that naturally discovered uranium must be enriched first. A method for doing this is via gas centrifuge, as shown in the picture. As in most fossil fuel power stations, in order to generate energy, steam is used to spin a turbine connected to a generator. The energy released from the fission reactions is used to heat water to steam. This steam is used to turn the turbine. Nuclear fission, while producing around 10% of the world's energy, remains a highly controversial power generation method. Opponents argue that this method is dangerous and poses many threats to people and the environment, citing disasters such as Chernobyl and the relatively recent Fukushima power plant. Opponents, however, argue that it is a cleaner source of energy than fossil fuels and is more energy efficient.
Nuclear fusion uses the same principles as nuclear fission to create energy. However, nuclear fusion involves bringing two atoms together to form a larger one as opposed to splitting a large atom into two smaller nuclei. Bringing two small nuclei together produces energy as the mass of the larger nuclei is less than the sum of the two smaller nuclei. The extra mass is expelled in the form of energy, which can, in theory, be harnessed. A nuclear fusion reaction releases around 4 times 10 to the 8 kilojoules per mole. Comparatively, a neutralization reaction produces just under 60 kilojoules per mole. Although nuclear fusion reactions require very large activation energy and temperatures in the millions of degrees, thus it is difficult to create and maintain a nuclear fusion reaction. There are two reactions currently being studied as a fusion reaction. Both involve the use of heavier isotopes of hydrogen atoms. Deuterium is a naturally occurring isotope of hydrogen, and as such can be found in water. Tritium, however, is radioactive with a half-life around 12 years and requires lithium to be produced. Many have attempted to achieve a stable, useful nuclear fusion reactor. These attempts have been successful at fusion, although the tests have resulted in more energy being used than created due to the high activation energy. The jet reactor is an example of this. The way nuclear fusion is currently conducted is through the use of plasma. Plasma is the fourth state of matter that can be created by subjecting a gas to a strong electromagnetic field. The key features of plasma include the ability to conduct a current and the ability to reach temperatures of millions of degrees Celsius. This makes it ideal to conduct fusion in. In an effort to expand upon the research, the ITER is being developed. The ITER is a thermonuclear fusion reactor that is being constructed in southern France. The facility is being funded by China, the European Union, India, Japan, South Korea, Russia, and the United States. Nuclear fusion as it stands seems hopeful and a reliable source of energy. However, the ITER is only an experimental project. Many more years of research and construction time need to be invested before humanity can harness the power of nuclear fusion. The current prediction by ITER scientists is to have a working nuclear fusion reactor providing power to the people by the 2040s.
Hydrogen is the most abundant element on Earth, so could potentially be a great alternative. Although it can't be found in pure form, hydrogen can be produced from other compounds such as natural gas, biomass, alcohols, or water. One immediate negative of hydrogen fuel, therefore, is that in all cases it takes energy to convert these sources into pure hydrogen. What definitely needs to be considered is the carbon footprint of the energy used to produce it. One way of getting hydrogen is from reforming fossil fuels. As oil and natural gas contain hydrocarbons, a fuel processor or reformer can split off hydrogen. This can be done with steam reforming or shift reaction. What I will focus on is electrolysis of water, which is also quite efficient at 50 to 80%. This is about 3 to 10 times more expensive than steam reformation of natural gas. For electrolysis, energy as electricity is required to split up the water into pure hydrogen and oxygen. There are several ways in which we could create electricity that doesn't use fossil fuels, such as nuclear power, hydroelectric dams, solar cells, wind turbines, geothermal power, wave and tidal power. Emissions can be majorly reduced by using processes this way to electrolyse water. An example in the world right now is the Bayswater Power Station in New South Wales, Australia, which creates electricity by using pressurised steam to run turbo generators. The only downside is that only around half as much electricity comes out of the fuel cell that was put in to produce the hydrogen in the first place. The rest is lost heat. One of the most potentially useful ways to use hydrogen is in electric cars or buses in conjunction with a fuel cell, which converts the hydrogen into electricity. They are far more efficient than internal combustion engines, and London now has a fleet of 8 hydrogen fuel buses running on the route RB1 between Covent Garden and Tower Gateway. What is a hydrogen fuel cell? In a fuel cell, hydrogen gas is channeled through the anode side and oxygen passes through the cathode. The platinum catalyst oxides the hydrogen atoms into H+ and electrons. The electrons pass around the external circuit, conducting electricity before entering the cathode. At the cathode, this is where the catalyst combines the H+, oxygen, and electrons into water and heat. There are some cons, such as using a catalyst is very expensive, and also there's specific humidity and pressure that's needed in the fuel cell. Furthermore, it's difficult to store hydrogen. But hydrogen does have great potential, and with more attention within the development of hydrogen fuel cells, it could be an excellent abundant and clean burning fuel for vehicles especially.
To conclude, There are many different kinds of energy alternatives, which each have their own pros and cons. Although there is not a single source that is world-saving just yet, an alternative to fossil fuels is essential. By encouraging further development in these areas, some of the problems can be overcome, giving us a more positive future for planet Earth.